All right, so we have been talking about hypothesis testing and we are trying to understand the Excel output and those values there in the Excel output. So just to remind that we have this table apart from the ANOVA table in the Excel output where these are the coefficients. So our beta 1 hat is 4.5 and beta 2 hat is minus 0.5. And then we have the standard errors. Standard error of beta 1 hat is 2.02 and standard error of beta 2 hat is 0.64 from the above table. And then we have t statistics. This is just the adaptation of the coefficients on the t scale because coefficients can be on any scale. For example, if I talk about this minus 0.5, it means in this regression, what does this minus 0.5 mean? The beta 2 hat. It means that if x rises by 1 unit, y falls by 0.5 units. If x rises by 1 unit, y falls by half a unit. So it's in the units of x and y. So the
Excuse me, sir. Few students are waiting. Can you please let them in?
okay, sure. So how big your beta 1 hat and beta 2 hat would be depends on what scale the numbers are. They may be in thousands and thousands. Sometimes you're talking about GDP as your y variable, so it's in millions and billions. So there is a need to adjust this beta 1 hat and beta 2 hat onto a normalized scale, and that's what we do when we adjust it onto the t scale. So this is our t distribution. Where in the center we have t equals to 0 and we have negative t values to the left of the center and positive t values to the right of the center. Now we when we do the hypothesis testing, we have two approaches. One is the confidence interval approach and another is the test of significance approach. Test of significance approach. In test of significance approach, we just see the p-value. We see the p-value and then we make a decision, right? So if p-value is less than or equal to alpha, we reject the null. Right? So that's the test of significance approach, and we look at the p-value in test of significance approach. Right? So we have a null hypothesis, that beta 2 hat is equal to 0, and we have an alternate hypothesis that beta 2 hat is not equal to 0. So it's a two-tailed test, and we try and find the p-value. Now, what is the p-value? P-value is simply locating your t-statistic, which is 0.77 minus 0.77 and plus 0.77 from the table, as you can see, and then finding the area in the tails. So whatever area in the tails is the p-value. So green area is the p-value of t equals 0.77. So if t is 0.77, which it is in case of beta 2 hat, you can see it from the table here, uh, then its p-value is going to be area in the tails separated using 0.77, right? So we have to locate this t statistic on the graph, and then we see what is the area under the graph. So we have two areas: area in the body, and then area in the tails. So area in the tails is the p-value of the t statistic, and t statistic is nothing but the adaptation of beta 2 hat onto a scale which is general and common, like t, right? So the what is the importance of having putting this 0.77 on the t scale? The importance is that we have a t table, and if we look into the t table, we can find the green area. Helps us get the p value, right? So let's see the table.
Sorry, I believe someone is trying to jet in.
Okay, so if let's have a look at the table and see
Uh,
the area.
Also, sir, this is the same concept which we discussed in the previous classes, right?
Yes, yes. So if we see, if we look at the t table, we are able to get what is the p value, and for that we need to know uh, only two things: that what is the sample size. In other words, if you know the sample size, you know degrees of freedom. So degrees of freedom is n minus k for t, and then n in our case was 5 and k was 2, so degrees of freedom was 3. So 3 degrees of freedom will make up a t distribution, right? And then uh, we will go into the t table and find out what is the p value. So let's see the t table now.
Excuse me, sir. I guess Navya is trying to enter. Can you please let her in?
All right, sure. So if we see t distribution in the Gujarati book, it looks like this, right? And the table gives us uh, the shaded area, right? So it says that what value of t gives a 5% area in the right tail, right? So if you look at the probability of 5% and for 20 degrees of freedom, you can see it is 1.725, right? So for 5% in the right tail, it is this much. Or these t values are also for 10% area in both the tails, right? So you have to understand this, that why there are two probabilities here. We have a 5% and a 10% area in the tails. And for 20 degrees of freedom, it is 1.725, which corresponds to both 5% and 10%. Why it is so? Because if you see only a right tail or a left tail, one tail, it would be, this value would give a 5% area in the tail. And if you look at two tails, then this value would give a 10% area in the tail, right? So in our case, degrees of freedom is 3. So we will look at the third row only. And what we want is what we can see 0.77. In this row, we can just locate 0.77. So because there is 0.765, which is very close to 0.77, still 0.77 is little bit higher than 0.765. So we can say that for a one tail, it would be 25, something between 10 and 25% area in the tails in one tail, and something between 20 and 50% area in the two tails, right? So we got our conclusion just by locating the number on the third row, because 3 is our degrees of freedom, and just locating 0.77 or any t value here. For example, had your t value been 2.5, had it been 2.5, it would have been between this value 2.353 and 3.182. 2.5 is in the middle of these two values. So you would have said that the p value would be in the middle of 2.5% and 5% for a one tail, and 5% and 10% for two tails, right? So in our case here, because we have 3 degrees of freedom, we will look into the third row of this table, and then we will see where is 0.77. What we found is it is in the middle of this number 0.765 and 1.638. Of course, it is very close to the first number, but it is in the middle of these two numbers which are there in the table. That means the p-value would be between, because it's a two-tailed test, so we will look at the bottom one, 50% and 20%, right? So something very close to 50%, because 0.77 is very close to 0.765, right? So it is very close to 50%. Of course, it is between 20 and 50%, right? So if we go and see our table here, so we are able to see here that p-value is very close to 50%. P-value is actually equal to 0.49. That's what we got from Excel. And p-value is greater than 0.2 and less than 0.5, right? That's what we got from the t table. But it is very close to uh, 0.5, because our number was very close to 0.77, right? So that the number that corresponds to 50% area, the t value that corresponds for a 3 degrees of freedom t distribution, the t value that corresponds to it to 50% area in two tails is 0.765, and our value is 0.77. So this is almost same, right? That means the area would also be very close to 50%. And you can see it is close to 50%. 0.495 is actually very close to 50% area in the two tails. So using the p values, once we found that it is between zero point 0.2 and zero point 0.5 from the t table, we can we will say that we cannot reject the null. We cannot reject the null, which was that beta 2 hat is 0. Why we cannot reject a null? Because of the rule. The rule says p value should be less than or equal to alpha, and alpha is 0.05, and p value is zero point 0.5, is between zero point 0.2 and zero point 0.5, which is greater than 0.05. So we have to we cannot reject the null, and we will go with the null, which means that our beta 2 hat is actually 0. So when our beta 2 hat is actually 0, we will not interpret this number beta 2 hat, that if x rises by 1 unit, y falls by half a unit. We will not make this statement here if when we are doing our research. Of course, in exam, if I ask you just interpret beta 2 hat, you have to write this statement, right? So similar is the case with the uh, beta 1 hat. You just have to find 2.22
So
on.
somebody is trying to let in.
Okay. So we can do the same exercise for beta 1 hat, where t statistic is 2.22. So if we have a look at the t table again, a t statistic of 2.22 would be for 3 degrees of freedom would be in the middle of these two numbers, 1.6 and 2.3. Of course, it is close to 2.3. 2.22 is closer to 2.3 as compared to 1.6. But it is in the middle of these two numbers. So we would say for a two-tailed test, the area is between 10 and 20%, but it is close to 10%. So you can see the p-value here for beta 1 hat, which says 11%. As I said, for beta 1, p-value would be between 10 and 20%. So, but it is close to 10%. So we can see that p-value is actually 0.11, which is close to 10%. So it's not it's not necessary to use the p-value from Excel or any other software. We can simply look at the table to get the p-values, and that is the test of significance approach. Looking at the p-value, if it is less than or equal to alpha, we reject the null. That's the rule. We just have to find what is the p-value, and we can get it from the t table. Once we got it, we can make our judgment whether to reject or not to reject null. So that was the t.
Sir, I guess Satvik is trying to let in.
Okay.
All right, sir. I guess maybe some connectivity issue. And another thing, sir, with respect to our like our understanding, you're basically trying to say that the higher the x would be there, the lesser. Uh, I mean, the higher the x, the more or the less would be the accuracy.
Higher the x. So what is x?
Sorry, not higher, not the x, but higher the alpha, less the accuracy.
Okay, so I'll come to this point.
Okay.
Yeah, I'll come to this point. All right, so that's the how to see the t table, and let us do one more thing here, which I wanted to do to make you understand how to see the F table. So because there is a p-value for the F also, let me share my Excel screen. So instead, so now we know how to see, how to get these p-values and make decisions. Now what about this p-value? This is also a p-value, isn't it? 0.495, and it is the p-value of the F statistic, which is zero point 0.6. And F statistic is used to say something regarding the null, whether all slopes are simultaneously zero, or at least one of them is non-zero. So when we are trying to reject or not reject this hypothesis that whether all slopes are simultaneously zero, we see the F, we calculate the F statistic, and we look into the F table to get the p-value of the F statistic and make a decision on whether or not to believe that all slopes are simultaneously zero. So let's see this zero point 0.6 in the F table, and we will need two things here. We will need the numerator degrees of freedom, which is 1, and denominator degrees of freedom, which is 3. So numerator degrees of freedom is the degrees of freedom of the ESS, and denominator degrees of freedom is the degrees of freedom for the RSS, which is 3. So keep in mind, numerator degrees of freedom 1, denominator degrees of freedom 3, and then we have to see zero point 0.6 in the F distribution. And then our goal is to get the p-value of the F statistic. So let us go to the F table, 0.613. So then we have this F table. You can see that the table shows uh, area in the right tail for a given F statistic. So if the F statistic is 3.14, then area is 5%, right? And basically there is degrees of freedom for numerator and 1 degrees of freedom in the denominator and 2, uh, and there are numbers 1, 2, 3, right? And then there are probabilities here, 0.25, 0.10, 0.05. These are the probabilities. Now, what in our case, what we will do is we will first see what are the numerator and denominator degrees of freedom. So it is 1 and 3. So we will see numerator degrees of freedom 1 here, and then 3 here, and then where is the intersection of this 1 and 3, and we find a set of values here. So if I take the screenshot of it just to explain you, it would be a good idea. And let me put it on my slide. Because now I can edit right over it. All right, so we will see where is 1 degree of freedom in the numerator, 3 degree of freedom in the denominator, and we will see the intersection. The intersection are these 4 values. So we have values in sets of 4, right? For example, for 5 degrees of freedom in the numerator and 4 degrees of freedom, we have this set 2.07, 4.05, 6.26. Now we are concerned with this box, these 4 values, and each of these 4 value corresponds to a probability. For example, 2.02 corresponds to 25% area in the right tail, then 10% area in the right tail is 5.54. F statistic of 10 gives 5% area in the right tail, and you can see 34 gives uh, this. Now you can understand from the logic that if this is the F distribution, you can think of 20 of 10%, 5% and 1% areas. So 5% area, so you can think of 5.54, and you can think of a value 10.1. So if I ask you which one would give a less area, smaller area in the tail, of course the bigger value. So the bigger the value is, the smaller the area in the tail, as you can see in these values, right? So it's simple to understand that what is the correspondence between probabilities and the values of the F statistic, because these values are plotted on the x-axis, and then probabilities are plotted as areas under the curve, and we can see the correspondence by looking at how big the value is. The bigger the F value, the smaller the area in the tail, right? So it's simple to understand. Now let us come to our case. In our case, our F statistic is 0.6. So we have to locate where is 0.6 in these four values. And there is no 0.6 here. But if we see the order in which the values are moving, so our value's smallest is even smaller than the lowest value here, right? So the lowest value is 2.02, so it will be below 2.02. That means area under the tail would be above 0.25, right? Had our value of F been 3, we would have said that area is between 25% and 10%, right? Because 3 is here in the middle of 2.02 and 5.54. Had the F value been uh, greater than 10.1, then we would have said that area in the right tail would be less than 0.05, right? That's what these numbers tell us. So in this case, because our F value is zero point 0.6, we conclude that area or the P value would be greater than 25%, right? So if we go and see our Excel output, it would show us the F statistic was not significantly different from 0. And you can see it is 50% basically. So it is more than 25%. So whether it is 50% or 26% or 25% or 6%, we are not going to reject the null unless p value is less than 0.05. So it doesn't make any difference to us whether the p value is 6% or is it 56%. They are both the same, because in both cases we are going to not to reject the null, right? So our result is not affected. So that's why that we can only see the table and reach a conclusion without having to know the exact p value of the F statistic or exact p value of the T statistic, right? All right. So one, I will come to the point what Priyank asked, that alpha is related to accuracy, right? I'll come to that point. But before that, I wanted to show you how to see the T table, how to see the F table. And then the last thing which I want to show before coming to those things, uh, I want to show how to calculate the lower and upper confidence intervals, right? So this part I've already copied into my PowerPoint presentation. So let me come back now. So here, uh, so let me copy this table from here and put it here for my explanation. So The confidence interval approach is the second approach. So we had test of significance approach, the p-value approach, and then we have confidence interval approach. I'm writing it in very bad way. So confidence interval approach. In this case, we develop a confidence interval and then we would check around the estimator, the value of the estimator, and then we will see whether null lies in it. So null remains the same. There is no change in the null. Whatever approach you are following, null says that beta 2 is 0. So in the population, x and y are not related, right? So that's the null. And alternate hypothesis is that it is not 0. That means that x and y are actually related in the population, right? So it remains the same. Now let us make a confidence interval. So we start with the mean, and mean here we start with the estimator. So our estimator is beta 2 hat, and we will plus minus something here. And that would be for a two-tailed test, T alpha by 2. Let me write it more clearly so that you can see. T alpha by 2 times standard error beta 2 hat. That's the formula. So once you're going to add it, and then you're going to subtract it from the estimator, and what you will get is the lower and the upper limits. So lower limit is going to be beta 2 hat minus T alpha by 2 standard error beta 2 hat. And the upper limit is going to be beta 2 hat plus T alpha by 2 times standard error beta 2 hat, right? So we get a lower limit and an upper limit, and this is 95% confidence interval because it depends on our alpha, and we have assumed our alpha to be 0.05. So when we are saying alpha by 2, it means we are talking about half the area, half the alpha, because there are two tails. And if somebody asks you what is the t value that gives an area of 5%, so your question would be where? There are two possibilities. Do you want a 5% area in both tails, or do you want 5% area in one tail? Because the value that gives a 5% area let me not write it here. So the value that gives a 5% area is the black line, and in that gives a 5% area in the right tail, and only in one tail, right? So if you want 5% area in both the tails, then you would have to shift it here, where this area would be 0.025, right? So that would be 2.5% area. So let me not confuse you by writing decimals like this. Let me write it straight, 2.5% here and 2.5% here. right? So this is the value, the green value, just I'm writing hypothetically here. Maybe this is 2.9 minus 2.9. So 2.9 is the t value that gives an area of 5% in both the tail. That means 2.5 in the right, 2.5 in the left. So that's 2.9. And then 2 is the value of t that gives an area of 5% in one tail, in the right tail in this case, because 2 is positive, so it should be the right tail. So we when this sort of question is asked, that for example, I'm trying to explain you what is this t alpha by 2, right? So if alpha is 5%, then t alpha by 2 means t 0.025, right? So what is the t value that gives a 0.025 area in one tail, right? That's what we are asking. That's the value that we are going to put here. So we will see the table for this. We will see the table, and for a given degrees of freedom. In our case, degrees of freedom is 3. So for 3 degrees of freedom, the question that we asked is, what is the t value that gives an area of 0.025, or alpha by 2, which is 0.025 because alpha is 0.05, that gives an area of 0.025 in one tail, in any one of the tails, of course, in the right tail. Because in generally in tables, it's the area under the right tails. So let us see that value from the table. So I'm going to go back to the table. So here is the table. And then I'll go to T distribution again. Here, this is Z distribution and this is T distribution. So what is the value that gives the area of 0.025? For 3 degrees of freedom, it is 3.182, right? 3.182. Because in two tails, it will convert to 5%. And in one tail, it is 0.025, right? So the value is 3.182. We got it from here. Now I'll go back and use this value, 3.182, in Excel. Now let me copy this on another sheet. Right? So what I'm going to do is, first I'm going to find T alpha by 2. And T alpha by 2 in Excel, I mean, we already know it. It is 3.182 because we saw it from the table. How to get it in Excel? You can simply write T dist, sorry, T dot inv dot two tailed. So I'm going to write 2t. So this is tinv 2t test. And what probability you're putting here? For example, you are putting, it's two tailed, so you're going to put the entire 5% because it knows that when it is two tail, then what is this 5% area? It will distribute it into two uh, tails, right? Then what is the degrees of freedom? 3, and you will get the same value, right? So we saw it from the table, and this we got from Excel. It doesn't matter, so I'm going to delete it because this is also 3.182444631, and again we already have had that value. So I can use this value because this is more accurate, the value I got from Excel. So that's my T alpha by 2, right? Now I'm going to form this the lower limit, lower 95%. And if you remember the formula, it was, in case of beta 1, it was beta 1 hat, which is 4.5, then minus standard error, the standard error of beta 1 hat times T alpha by 2, which is 3.182, and we got the lower limit of the 95% confidence interval of beta 1 hat. You can get upper 95%. Let me not write this 95, let me write beta 1 and beta 2. So this is upper limit of beta 1. Now upper limit of beta 1 again will start with the value of the statistic, which is beta 1. So which is 4.5, and then this time I'm going to add this whole thing, which is the product of standard error times t alpha by 2, which is 3.182. So we got 10.93. If you see, 1.93 and 10.93 are indeed the lower and upper confidence, uh, lower and upper limits of the confidence interval, 95% confidence interval for beta 1 hat. Now we can do the same for beta 2. So it's straightforward. There's no change in the formula. Just use beta 2 hat and then subtract the product of standard error and T alpha by 2 to get the lower limit. And in order to get the upper limit, you can use the same beta 2 hat, and in that case add the product of the standard error of beta 2 hat and the T alpha by 2. So you would get minus 2.55 to be the lower limit and plus 1.55 to be the upper limit. And I'm going to make it yellow. These four numbers are also the same, which are these. So I don't know why Excel repeats these last four numbers. So I'll make them all yellow now. So that's how we calculate the lower and upper limits of the 95% confidence interval. Now I'll come to that question, that what is it? What is this confidence interval? What does it mean? What is the meaning of alpha? How can you test using the confidence interval approach? And I'm sure there would be a lot of questions coming in your mind. So uh, now I'll clarify those. All right. So now I think a good idea would be, okay, let me just tell you the meaning of the 95% confidence interval. Okay, let me tell you the rule first. So the rule is that if this is the limit, so beta 1 would be between minus 1.9308 up to 10.9308, and beta 2 would be would lie between minus 2.554 and 1.5542. So we have this lower and upper limit for beta 1 and beta 2. So and the alpha associated is 5%. So confidence level is 95% in this case. So what does it mean? Now, what is the rule here? How do we reject and not reject the null? Just by looking at the confidence intervals. What you have to do is you have to locate a zero. Locate zero where is zero, right? If zero lies in, let me write it in red color. If zero lies in confidence interval, reject, don't reject the null. Don't reject the null. Simple rule, right? So we had a rule that if p value is less than alpha, reject the null. Less than equal to alpha, reject the null. That was in the test of significance approach. We don't have to look at the confidence interval in that approach. But if we don't have the access to p-value, and if we want to take up the second approach, not the first approach, the confidence interval approach, you can make your decision using that also, right? In that case, we have to find the lower and upper limits of the 95% confidence intervals of the estimators, and of the population parameters rather. And then you have to see whether zero comes lies within the interval or not. If zero lies in the interval, you can't reject the null, because null says beta 2 is zero, and you can't reject it because zero is coming in the interval. So beta 2 is zero. So you can't reject the null. You would say no, null can't be rejected, and we go by the null that beta 2 is zero. Right? So in both the cases, we see that there's a negative value and there's a positive value. The lower limit is a negative value and the upper limit is a positive value in both the cases, here as well as here. So we will not be able to reject the null that beta 1 is 0, and we will not be able to reject the null that beta 2 is 0. So in that case, we will go with the thought that beta 1 and beta 2 are both actually 0, because we could not reject the null. And that was exactly the result we got from the test of significance approach also, because the p values for both of them were greater than zero point zero 0.05, and we wanted them to be less than or equal to 0.05 to reject the null, but we couldn't do it, right? So we got same results. We got same results from both test of significance approach and confidence interval approach, and we will always get same result, it whichever approach we use, right? So just have a good reading of these things which we discussed. Of course, I'm going to end this. I want to end this hypothesis testing part rather quickly. I've given a lot of time to it, so I think one last class, and then and you can ask whatever questions come to your mind regarding the hypothesis testing part. There is one full chapter for hypothesis testing in Gujarati, but I did not use that. I just explained you with reference to our Excel output without using Gujarati here, because uh, I thought that I wanted to finish it in one or two classes, but somehow I could not do it. Anyways, so um, you can ask questions, whatever questions come to your mind next time.